Hello and welcome. This is Dave. Just kidding, it's Matthew. And for today, I have a very interesting idea. Um, my idea is ChatGPT versus mathematician. Yes, I am calling myself a mathematician. But of course, you've read the title of the video, you know what's going on. So we have three integrals. I'm going to solve all the integrals, and then we're going to move on to ChatGPT and see if it can solve the integrals. So integral number one is very easy and straightforward. I can say pretty much the same thing for integral two. It's a bit harder than integral one. And then integral 3 jumps up in difficulty. It's much harder than 2 and 1, but it's still, I guess, pretty easy. No, I wouldn't say it's that easy, but it's okay. So let's not waste any more time. Let's hop into this video, but first, like and subscribe. So we'll go ahead and start with the easiest integral first to get it out of the way. So we'll start off with the first integral. Now this integral is very straightforward. We're just going to use the reverse power rule. I'm stuttering, it's okay. The reverse power rule. So we have an exponent of 1. So we're just going to add to that 1 plus 1, divide by the same thing, 1 plus 1. Or, of course, 2. I know. I'm very good at math. I did 1 plus 1. And then we'll evaluate at the limits for x, which then equals 1 squared over 2 minus 0 squared over 2, which, of course, this just collapses to 0, which then just equals 1 over 2, or 1/2. So, therefore, this integral is equal to 1/2. So first integral out of the way. Now we're gonna move over to ChatGPT. I keep stuttering, and see if it can solve it. So let's do that right now. So here we go. I'm going to send ChatGPT. I keep stuttering. It's okay. It's okay. So I'm going to send ChatGPT the integral right now. Let's see if it can solve it. Okay, doing well. And there we go. We have the answer. So it is actually 1/2, so it got it right. Very impressive, of course. But then again, it was the first integral. It was pretty easy. Maybe I should go to a harder one. Okay, so let's move on to the integral number 2. Now it is a time for integral number 2. The integral from negative pi to positive pi of sine of x. Now for this integral, we're going to use a very interesting thing. Integration by symmetry. If you've caught this, that's very good. So, what integration by symmetry is, for an odd function, because we know sine of x is an odd function, the integral from negative a to positive a of an odd function, so I'll just write it as odd of x dx, this right here equals 0. So what is an odd function? Well, definition of an odd function, so f of x, if we replace x with negative x, so f of negative x equals negative f of x. This implies that f of x is odd. So we will have to test sine of x. Now, sine of x. What is sine of negative x? Well, since sine is an odd function, this equals negative sine of x. Which by definition, that of course does make sine a odd function. Of course, I was just saying that we already know that sine is an odd function by trigonometry. And we have a negative pi to positive pi, so therefore this integral will equal 0. So integral number 2 equals 0. Now let's see if ChatGPT uses symmetry or if it just goes through the process and gets 0. Now let's go over to ChatGPT. So I went ahead and put in the integral into ChatGPT, and we see it, but it did not use I can't speak, symmetry. I forgot the name. It did not use symmetry in this integral, but it did find that it is 0. So it got the integral right, but it did not use symmetry, which is very sad. But still, it got the integral right. I'm sorry that I was stuttering a second ago. I talk way too fast. But it got the integral right, so there we go. Let's move on to integral number 3. Now it is time for the third integral. Yes, the third one. Now this integral is going to be a bit harder. Yeah. So let's not waste any more time. Let's go ahead and hop into the third integral. Now, the first thing I want to do is simplify this integral. What I mean by simplifying the integral is that we have a sine of x times cosine of x. But if we recall the double angle identity for sine of 2x, it's equal to 2 sine of x times cosine x, which looks very similar to right here. So what we can do is multiply 1/2 on both sides. So 1/2 on this side, and this 2 and 1/2 would cancel. So there we go. Sine of x times cosine of x equals 1/2 sine of 2x. So I'm going to go ahead and apply this to integral number 3. So here we go. Here is the more simplified version of integral 3, right here. And all we did was use a double angle identity for sine of 2x. But after I did this, I didn't really know what to do. I was stuck. I tried a little bit of Feynman's trick, and I placed the alpha parameter right here in the exponent of e to the negative x squared. It didn't really work out for me. So then I tried placing it in the sine function right there. And I still really didn't know what to do. So then I, of course, differentiated it, and still, it was confusing to me. I tried a couple things, it didn't work. But then I tried integration by parts, and it worked. So enough of me speaking about what I did, I'm going to show you what I did. So first I will define a function. So here we go. This is the function I defined as f of alpha, with alpha being a parameter inside the integral. But now we observe a couple things. That 1/2 of f of 2 is just equal to integral number 3, which I'll just write as 3. That's just referring to integral number 3 right here. So we know that 1/2 times f of alpha equaling 2 is our third integral. Another thing we can observe is if we plug in alpha equals 0, so f of 0 equals 0. And that's because if we replace alpha with 0, well, sine of 0 is 0, so therefore the entire thing would collapse to 0. So f of 0 equals 0, so I'll place this up here. Let me place this right here. Sorry about that. Okay, so now we have an initial condition, basically, and our target integral. Now it's time to differentiate it, so I will do this right now. So f prime of alpha is this guy. And this is the Feynman's trick I was talking about. Or if you don't know it as Feynman's trick, it's also called Leibniz, or the special case of Leibniz rule for differentiating under the integral sign. Where if we try to differentiate an integral, right here, or an integral function, I guess, and we don't have functions of alpha, our parameter that we're differentiating with respect to, in the limits, then we can go ahead and just take in the derivative inside of the integral, but then it becomes a partial derivative with respect to the same parameter alpha. And this derivative, the partial derivative, is very easy. If you've taken any calculus 3, you will know this. It's not much different than a regular derivative. And if you differentiate, you'll find yourself with this new integrand, which doesn't look any better than our original f of alpha right here. But if you do an integration by parts, it becomes easier because of this extra x right here. And let me write down what I'm thinking. We'll do the DI method. And we'll go ahead and differentiate the cosine function with respect to x. Okay. Yes. And then we'll integrate x times e to the negative x squared. And this integral is very, very easy. If you evaluate it, you'll find yourself at negative 1 over 2 times e to the negative x squared. There we go. And if we recall the DI method, we're just going to multiply that one and then evaluate this integral right here. There we go. So let me get rid of this, and I'll write down what I'm thinking. So after doing integration by parts, we find that our f prime of alpha is now equal to this. But let's evaluate this side right here. If we plug in, well, if we take the limit as x goes to infinity of this thing, we'll get a 0. So therefore, this thing is equal to 0 minus negative 1/2 times cosine of 0 times e to the negative 0, which, I'll write this down, cosine of 0 times e to the negative 0. Of course, e to the negative 0 is just 1, and cosine of 0 is also just 1. And 0 minus negative 1/2 is just going to be positive 1/2. So therefore, this thing right here is equal to 1/2. Okay, so we can replace this with 1/2. Now, this integral looks very familiar to me. That's because if we look at f of alpha, it's the same integral. So we can replace this integral with f of alpha. So now we have f prime of alpha is equal to 1/2 minus alpha times f of alpha over 2, which is a differential equation, a linear first-order differential equation. So we've turned our integral into a differential equation, which is really cool, actually. So here we go. This is the same differential equation we had before, except all I did was rearrange a little bit. And then I went ahead and solved it. Which, if you don't know how to solve first-order linear differential equations, I suggest you go over to the organic chemistry tutor. He has a very nice video on them. But I'll leave it as homework for you. Now, we see in f of alpha, we have this integral right here, which we'll have to use the imaginary error function. So I will show that right now. Now, here is the imaginary error function I was talking about. This integral looks very similar to this one, except we need to make a substitution to make them look pretty much the same. And what substitution is that? Well, we'll let alpha equal 2 times x. Therefore, d alpha equals 2 dx. So now we have 1/2 the integral of e to the alpha squared over 4 is now equal. We have a 2 on the outside, so this 1/2 and that 2 will cancel, and then we'll have a x squared dx, which we know this is equal to square root of pi imaginary error function of x divided by 2. And we won't worry about the plus c because we already have the constant right here. So there we go. Except we need to go back to alpha. So we have just an x. Well, we know that x equals alpha over 2. Because if we divide both sides by 2, we get x equals alpha over 2. So we'll just have an alpha over 2. There we go. This integral is now equal. Let me go ahead and get rid of this. Delete. To the square root of pi e r f I, or the imaginary error function, of alpha over 2, all over 2. But remember, we have an initial condition, which is all the way up here. We have f of 0 equals 0. So we'll apply that right now. Let me do this. So f of 0 equals 0, which also equals e to the 0 times what exactly? Well, square root pi over 2 times the imaginary error function of 0 plus c. Well, this is e to the 0 is 1, and the imaginary error function of 0 is 0. So therefore, we just have 0 equals c. So c equals 0. So we get rid of this c right here, and there we go. F of alpha is equal to this thing. But we know that, hold on, let me go ahead and move this out of the way. Actually, just delete it. We know that 1/2 f of 2 equals the third integral. So what we need to do is multiply 1/2 on both sides, so we can just bring it in here, and then put in a 2. So this would be 1, and this would also be 1. So here we go. Integral number 3 is equal to the square root of pi times the imaginary error function of 1 divided by 4 times e. So now it's time to go over to ChatGPT and see if it can solve it. So I went ahead and asked ChatGPT to solve the integral, and we see it gets the trigonometric identity right, the double angle identity for sine of 2x. It got that right. That's very nice. But sadly, it gets the integral wrong. So therefore, mathematician beats ChatGPT. I hope you enjoyed this video. I hope you learned something from this video. Please do like and subscribe, and have a good day.